Okay, so let's illustrate this kind of sequential approach. And remember, these are what we're going to call type 1 sums of squares. To do this, let's go to the part in the book where he talks about this. We're going to take a look at that amylase data again from chapter 8. Remember that there were three factors in this experiment. There was the amylase temperature, the variety, as well as the growth temperature. We looked at this to look at interactions. This was actually a chapter 9 example that I think we need to touch a little bit more on because this is a really complicated example, I think. But notice we have these three factors in the model, and suppose that the first observation in growth temperature 25, analysis temperature of 40, and the variety of B73 is missing. So we'd have unbalanced data, or Gary is actually just making this unbalanced for illustration purposes here. So if we separate out just the growth factor in the model, we can look at the error sums of squares that are type 1 for factor C. I shouldn't say error. Factor sum of squares for type C. So here are some model pairs that we could consider. The sums of squares for factor C is computed as that difference in the error sum of squares for a pair of models differing only in their term C. So we could have a lot of such models to point to as our base models, so to say. We'd have one, which is, remember, one is just the grand mean and C. Well, we wouldn't use that one for adding C. I shouldn't have put that in there. The grand mean and A, the grand mean and B, then things like this, the grand mean and A and B, or the grand mean and A and B and A-B interaction. So these ones here that don't include C up to this point, I think are really interesting ones to look at, and they're actually detailed below here. So using these sums of squares for C computed using these model pairs given here are shown. The data is actually on a log scale because a log transformation was needed for this data, if you recall. But we see the additional heterogeneity accounted for by inclusion of term C given just the grand mean. So we see the greatest effect there. Given the grand mean in A, we see a diminished return on including C, which makes some sense. But then if we have the grand mean in B, we see another change. Grand mean in A and B, we see another change. And then if we have AB and AB interaction, we see something yet different. All five of these, in fact, different. And we see some, look at the difference between the base model being the grand mean in A or the grand mean in B. There is a substantial difference there. And so we need to state which one you're using at any given time because it really does make a difference. So we need to be also very systematic about how we compute these because this seems arbitrary, doesn't it? Without a good justification or a good schema for doing this, I would not really advocate using one or the other. We need some algorithm for helping us do this in a way that makes some sense and seems justified in the data set context. So we have some simple choices. The simplest way to think about this is just to state we're going to use sequential sums of squares only. Okay, this is again that type 1 sum of squares. That's where we left off in the notes last time, if you recall. So for sequential sums of squares, we're going to specify that model and the sum of squares for any term adjusted, given the terms that precede it in the model. So if the model is the following, we've got AB interaction, and C, then the sequential sums of squares are A given 1. Notice A and B and C are arbitrary, so we're just starting with A. It's just whatever your first denoted factor is. Then B given 1 in A. Then AB given 1AB, and then C given 1AB. Notice that if you specify the terms in a different order, you're going to get a different sum of squares. So for example, if our terms are ABCAB, which actually this parameterization or order, I should say, makes more sense to me logically. because I would not consider higher order terms before I've considered every lower order term in the model. That's just a reasonable way to approach it, I believe. Then we'd have the sum of squares for A, given the grand, B given A1, C given 1AC AB, and then AB given 1 ABC. So these are going to be different than these, right? Make sure you understand why. The two models that include the same terms but in different order will have the same estimated effects and treatments, however. But if we include terms that may have different estimated effects, but they may include terms that have different estimated effects for the terms they have actually in common. So the consequence of that is that this order and that order will have the same alpha i's, but this and this may have different alpha i's because of the exclusion of the AB interaction. Okay, so we just saw from that example in the book that when we have unbalanced data, we're going to get a different decomposition for terms that are included in different order for that sequential construction of the model. For example, B adjusted for A is not the same thing as B adjusted for AC, but we saw that in detail in that last example. Building the model means selecting our main effects and interactions required to build the mean structurally. Gary, if you read the book, he is a big advocate for hierarchical models, and I really concur. I think this is a good, solid way to go about it. So this means for any term x, we choose the base model, the largest hierarchical model that doesn't include x. This introduces a new kind of sum of squares that we need to talk about. This is called type 2 sum of squares. I like to think of it as the everything but sum of squares. So if we consider, for example, the type 2 sum of squares for this particular model, notice in this particular model we have the main effects, two-way interactions, and three-way interactions. Okay, so then if we're adding, say, the term A, the everything but includes these, because that's everything but terms involving A. Verify that, okay? We include that. Well, that is our term we're wanting to add, so we don't include that. We include B, we include C. We don't include this because it involves A, but we do include BC, but we don't include this because it includes A, or this because it includes A. Similarly, the type 2 sum of squares for B is everything but B. Type 2 for C, everything but C. Then we get to the interactions. So this is specific not to C any longer, B or A any longer, A or C any longer. We need to be careful here. So we say everything but the term AC. So that will include the lower order terms including A, including C, and it can also include the interactions that involve A and C but with interacting with levels of B. But it does not include the ABC interaction because that does include expressively the AC term. Does that make sense? Make sure it does before you come to class. Then including everything but BC, everything but AB, and then the easiest one I think is everything but ABC because that's everything else in the model. It is possible to figure out what hypotheses about treatment means are being tested in type 2 and what its hypotheses and contrast mean. However, this can be really difficult to show and it's real tedious. And it's really just easier. I really like the advice of the author here, of Gary. Does adding this term to my base model improve fit? That's what these sums of squares, type 2, are really telling you. Well, you really want to see the hypothesis? So in the notes, seriously, you want to see these? Okay, we'll do it for a 2-factor. We're going to make sure we carry this out with that gender degree example that we deal with in class, because this I think is interesting, but like I said, I don't want to do this in every problem I ever do in class because we'll never get done with all of these problems if we are so detail oriented on these. We just need to maybe work it out a couple times and then trust that this is what's happening behind the scenes, even in unbalanced designs. So consider a two-factor design. Much like what we have in class, our weighted row means are the following. So notice these Nij's do not have to be equivalent. We're allowing unbalanced data here. Similarly, these Nij's do not need to be equivalent. They can be unbalanced. Now we can form the weighted averages for columns, but use your row weighted averages for the cell means instead of the real cell means. Because remember, this is a linear model, so we're estimating the real truth, and we have to get away from actual numerical mean estimators. That isn't telling us what our model-based means are any longer. So we use these weighted averages to compute those cell means. So we see, notice the notation here, it's a little hokey looking, but it's implying that we're summing over the J here, and we're summing over the Y here because we have to use those weighted averages for the cell means, for the I star cell means, okay? But we're doing it for each J. So then our type 2 hypotheses for B adjusted for A would be the following, that whatever level of B indicated by this J right here, the second indice, is going to be the same for all J, is going to be equivalent to this average of the cell means for all J. I should say that differently. So remember, this average for the cell means is the average of each weighted effect mean for A, weighted according to the schema being used at each level of J. Okay? These, again, I want to point out, if you just go to the data and compute the numerical means, it is not the same as your actual cell means. So you need to be careful. So what this type 2 hypothesis for B is actually testing is whether or not, is asking, is the reason column averages differ is because they are different weighted averages of the row weighted averages. Yes, that's correct. So see how it's a little bit more complex now when we start considering these everything but type 2 type tests. Okay, so there's yet one other third type. Type 3 is what is often referred to as standard parametric. You'll see this language in SAS. And in SAS it's called type 3. Type 3 tests, I think, have a lot of good intuition behind them. For example, they're simple, okay? So that's appealing at some level. A type 3 hypothesis could be something like this. The effect at levels I are all 0 for some factor. Testing depends upon the parameterization, though, when we're using type 3 sums of squares. So this works for the basic equally weighted effects add to 0 parameterization that we've been using all the time up until the end of these factorial chapters. And if you really think that equally weighted effects that add to 0 parameterization is correct to be using, then you can use type 3. For a standard parametric model, the base model for term x is all terms except x. So this is non-hierarchical in nature. For example, if we go, let's go this way. If we're testing, say, A, we not just have the everything but terms, but every other term that could be in the model. Okay, that's the difference. We can construct type 2 and type 1 sums of squares in R, but in R we don't really construct type 3, and I don't know that we want to anyway. So in R, the term A colon B is going to force the modeling of the means for the A-B combinations. So if we already have A and B in the model, that would be the A-B interaction. But if A and B are not in the model ahead of A colon B, then whatever's left out is going to get thrown in with the pure interaction.